சார் 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 ஸ்டார்ட் பண்ணிடலாமா சார் வர்றப்போ சார் சார் ரமேஷ் சார்
சொல்லுங்க.
சார் ஸ்டார்ட் பண்ணிடலாமா சார்?
யா
Okay sir. Very good afternoon to one and all present here. It's my immense pleasure to welcome our distinguished chairperson, Dr. S. Ramesh, Professor, Presidency University, Bangalore, for this third international conference on materials, manufacturing, and mechanical engineering for sustainable development, ICMSD2020. Welcome you, sir. And I also welcome all the participants from different colleges and universities for this international conference. It's my privilege to introduce our chairperson, Dr. S. Ramesh. He has graduated with a bachelor degree in mechanical and production engineering from Annamalai University and obtained his master degree in mechanical engineering with the specialization of manufacturing from IIT Madras, Chennai in 1997. He received a doctorate degree in mechanical engineering from Anna University in 2008. He has served Ethiopia for 2 years from October to August 2005, Mekelle University. He had also worked in Sultanate of Oman for Salalah College of Technology from November 2008 to August 2010. He has held various administrative positions in premier institutions. He received the Best Administrative Award 2016 from Dr. Kalam Educational Trust, Chennai. He is currently serving as professor in the Department of Mechanical Engineering, School of Engineering, Presidency University, Bangalore. He has 3 years of industrial experience and 25 years of teaching experience. He is an active researcher in the field of manufacturing engineering, and he has presently guiding 9 PhD research scholars under Anna University and 2 PhD research scholars under Satya University. He produced 6 PhD research scholars and contributed more than 100 publications in the international journals, national journals, and conferences. He was recognized for the inclusion as biography in 2013, 13th edition of Margus Who's Who in the World. He has participated in various seminars, symposiums. He visited various countries like Ethiopia, Sultanate of Oman, Malaysia, UAE. He is member of IE, IST, ASME, PMAI, AESI, SAE India. He received various awards: Best Administrator Award 2016, Reviewer Contribution Award for 2 times, Best Presenter Award, Best Teacher Award. So thank you for accepting our invitation, sir. Thank you, sir.
Yeah, thank you, Arun Kumar, for your wonderful introduction. Anyway, so this Arun Kumar, how actually this is only 5 students, okay? As per the sequence you are going to call, or
actually இந்த ஷெட்யூல்ல இருக்கவங்க யாரும் இல்லை சார். பகத் சிங் இதுல இல்லாதவங்க தான் பேப்பர் இப்போ இருக்கு சார். நம்ம ஃபர்ஸ்ட் அவங்களை ப்ரெசென்ட் பண்ண சொல்லியிருந்தோம் சார்.
But then the data and all, can I type?
நான் டைப் பண்ணி உங்களுக்கு அனுப்பிச்சுட்றேன் சார்.
Okay.
I can type.
Okay.
So Bhagat Singh sir. Bhagat Singh. You can unmute and come into that presentation mode. Bhagat Singh sir, are you ready? Okay. Tamil children?
Yes, sir. I'm hearing.
So you are ready?
Yes, sir. Of course.
Okay. You can present now.
Okay, sir.
அது மனிதன் நினைக்கிறேன்ல, அவர்கிட்ட வச்சு சொல்லுங்க. எடுத்துட்டு போவாரு.
Welcome you one and all. So I'm audible to you?
Yeah, your voice is audible.
Yeah, okay.
Can go ahead, Tamil Selvam, no problem.
A very good afternoon to one another person here. My paper is on mechanical and water absorption properties of Calotropis zyhantia plant fibers, reinforced polymer composites. My paper ID is 9135. Here we are going to present an over abstraction of my work. Utilization of natural fiber in polymer matrix composite material for research purpose and industrial application has witnessed a steady growth during the recent times. In this work, what we are going to do means we will take the Calotropis zyhantia fiber as a reinforcement for making the composite material, and then we will go for the compression molding process. In the compression method, we will take in compression molding method, we are used to fabricate a composite laminates that were subjected to water absorption and a mechanical property testing, such as flexural, tensile, and impact testing. In this work, we will take 4 tests. First one is the flexural and tensile and the impact. Impact is isoid impact, we will take it, and then water absorption test, we did it. And then what we are observed from the experimental result that the water absorption and mechanical characteristics of the Calotropis zyhantia fiber reinforced composite were on par with the other natural fibers reinforced composites, which were experimented in the past literature studies. In introduction part, we know the composites and what we are going to do it. Mainly we will take the Calotropis zyhantia plant. In that we can able to extract 2 types of fiber. One is from the bark fiber and another one is from the seed fiber. Here we are going to take that the Calotropis zygantia, a bast fiber. And then we will go for that used as an LY556 epoxy resin and HY951 Horner. Why we choose this means, when you take that LY556 epoxy resin, it is a solvent-free resin, and also it will give a medium viscosity, which will be easily go into that fiber and will get more interfacial bond. And we will take the HY951 Horner, which is able to get very high rigidity purpose. We will take and we will do the mixture in a 50:50 ratios here. And then we will go for a compression molding. Most of the literature are done in the hand layup method. We will go in compression molding because of to get an uniform when going to apply load during the fabrication laminates. We will get an uniform load throughout that entire composite laminates. And then the flexural strength. In flexural strength, as per the ASTM standard D790, we prepared a specimen length into breadth into thickness of the dimension of 125 into 12.5 into 3 mm thickness. And we will use the gauge length of 100 mm, and we applied load cell of nearly 10 kilonewton. And approximately the rate of loading is 5 mm per minute. We did it. And then tensile strength, we used the standard of ASTM D638/10. We prepared a dimension of specimen 165 into 25 into 3 mm thickness. We did it, and we used a gauge length of 100 mm. We will go for a universal testing machines, and a cross head speed nearly 5 mm per minute. And then impact test. In impact test, we used isoid impact test. In that, we are using the ASTM standard D25610. The dimension of specimen we prepared 62.5 mm into 12.5 mm into 3 mm. And then we will go for the water absorption test. We used a standard of ASTM D570. Nearly we are taken at initially 10 gram, and then we will go for the water absorption test. Normally we will calculate. How we calculated means water gain percentage we will calculate. How it calculated means the ratio of when we subtract the wet weight minus initial dry weight by initial dry weight into 100, we will get it. I will tell elaborately during my experiment. And then fiber extraction process. This is the Calotropis zygenta plant, which will be available around Tamil Nadu. We will get it, which have a least vegetative values. So we will choose the Calotropis zygenta plant, and the density is also in very low values. Okay, nearly 0.56 gram per cubic centimeter. The density is very low. And then we will extract Calotropis zygenta bark stem. We will remove the leaves and the petioles. After that, we will achieve the Calotropis zygenta bark stem. And then we will go for a water rating process. Why we are going for water rating process means we have to extract the inside, the fiber. Okay, nearly we will dip in water nearly 7 days, and then taken for sunlight for 2 days. And then due to that, water is penetrate due to the capillary action. The water is penetrate into a stem, and fibers are come slightly outside. By using a mechanical method, we will extract the fiber like that after a water reading process. And finally, we will get a cumulative of fibers, the Calotropis zygenta bark fiber. Generally, when we are going for a Calotropis zygenta plant, we can able to get two types of fiber. One is from fruit and another one is from bark stem. And then when we are going for fabrication of composites, we are used a resin, LY556 epoxy resin. I'm already told you. The main reason we are used this is a solvent free and which have a medium viscosity. And then we are using the HY951 Horner, which have a high rigidity. It will give, and we will achieve a final composite plate. We will achieve it by using a compression molding process. This is a test result. First one is the flexural strength and the modulus of Calotropis zygenta bark fiber. First, if you see the analyzing from the figure, the flexural strength, it will be taken from nearly 60 megapascal to 80 megapascal. When you are talking about a flexural strength, is also known about a modulus of rupture. Here we are going to define it. How we are going to define means the stress in a material just before it yield in a flexural test. It normally is taken from 60 megapascal to 80 megapascal. From the figure, we will get it. When we are going for flexural modulus, it's nearly 6.55 gigapascal to 8.86 gigapascal. If you take in the flexural modulus, is normally is a bending modulus. We will tell it. Okay, it's an intensive property. It's a ratio about stress versus strain. In that flexural deformation, we will get it. When we are going for a flexural modulus, the tendency for a material to resist the bending, we will take it. In the analysis, we will eventually take nearly 6 samples. In that, you can see when going for tensile strength and modulus, the tensile strength is nearly 41 megapascal to 58 megapascal, the variation. If you observe the graph, we will get nearly 41 megapascal to 58 megapascal. What we are getting in tensile strength means the maximum load that a material can support without fracture when being stretched divided by the original cross-sectional area of the material. We will get it. When we are going for a tensile modulus, nearly 212 megapascal to 292 megapascal. Normally, if you see the tensile modulus is a ratio of stress along an axis to strain along that axis. If you see about the stress is here, the force by unit area, and we will take it. Why we take that tensile modulus? The reason behind is when we are going for tensile modulus is used to predict the elongation or compression of an object as long as the stress is less than the yield strength of the material. And then we will go for the impact strength. In the impact strength, the highest impact strength is observed. The energy is observed by the calotropist Ziganda fiber composite is nearly 10.4 kilojoule per meter square. And observing the graph, we will get the lowest impact energy observed by calotropist Zyhantia fiber of composite is nearly 8.8 kilojoule per meter square. And then when we are going for, finally we are going for the water absorption test. The water absorption test, we will take the calotropist Zygantia normal fiber and from the composites. If you are observing the graph, normally the calotropist Zygantia fiber observing in a higher amount of volume of fraction of water molecules. The reason behind it is the hydrophilicity nature of the fiber. Generally, the natural fiber having a hydrophilicity nature. Here, due to that hydrophilicity nature, the calotropist Zyhantia fiber observed a higher amount of water molecules when compared with calotropist Zyganda fiber composites. And conclusion, the tensile strength and modulus were found to be better for calotropist Zyhantia fiber composites due to enhanced load carrying capacity of the calotropist Zyganda fiber. And second point, a calotropist Zyhantia fiber reinforced composite material exhibited better flexural strength and modulus, the value of 87.88 megapascal and 8.86 gigapascal respectively. I am already elaborately told in the graph. The maximum impact strength recorded by calotropist Zyhantia fiber composite is 10.4 kilojoule meter square. From the experiment, it is concluded that the rate of water absorption of calotropist Zyhantia fiber is higher than the composite. It's mainly due to the reason of hydrophilic nature of the calotropist Zyhantia fiber. Overall, it would be stated that calotropist Zyhantia fiber reinforced polymer composites are very efficient material and substitute that are much suited for various application in domestic, automotive, and then interior and exterior components. These are a reference we did it.
Okay. Tamil Selvan.
Yes, sir.
Actually, you go to the first page, first slide.
Yes, sir. Abstract.
No, the title. Yes.
Oh,
Here, actually, your name is Tamil Selvan and Ramesh is there. Who is the real contributor for this work?
Dr. M. Ramesh, sir.
M. Ramesh. Okay. You are working in Kalyan Institute?
Yes, sir. Yes, sir. He's a vice principal.
You are
I'm
working?
an assistant professor, sir.
You are assistant professor. Right. What is your role in this work?
I'm collecting that fiber, extracting the fiber, sir.
Extracting that fiber. Okay.
Yes, sir.
Okay. Then I want just a simple thing. The water absorption test. Okay.
Yes, sir.
So how to conduct water absorption test? Just for the people they are attending this session, no? For them, just you can tell what is water absorption, how to conduct water absorption test.
Yes, sir. In water absorption test, we can use the water absorption tester machine we are used. Nearly, we will take the 72 hours water absorption total time. In the 72 hours, we will record it for every 4 hours. In mainly, how we are to calculate it, water absorption means, from the graph I will tell you in a detailed manner. Normally, when we are taking that weight gain, how much the weight gain we have to take in a percentage manner. The weight gain percentage which is equal to wet weight minus initial dry weight by initial dry weight into 100. This is a formula, weight gain percentage. Normally, what we are doing means at initial stage, we take the 10 gram of the calotropis ziganda fiber and also the composite. 10 gram we will take at initially. We will dip in the water, and after 4 hours, we will take how much weight is there. And then we will record it for every 4 hours. We will nearly taken for 72 hours. We will taken for periodically for 4 hours once. We will take the calculations. And then we will calculate what is the wet weight, and we subtract from the initial dry weight, and we will get the weight percentage.
Okay, this is actually some weight which is added in the composite, right?
How much the water is absorbed? What's the capacity of that water is absorbed? We have to calculate in a volume of fraction.
Okay. Then, if water contamination is added in the material in the sense, there is a possibility of other failures. Okay.
Yes, sir.
So, have you concentrated that other failures? That means it may give strength. Okay, it's good, right? But at the same time, it may damage due to some other functionality of the composite. Okay.
So normally, when we are saying about natural fiber composites, the tendency of fiber is in a hydrophilic nature. Mainly due to the hydrophilic nature, it will able to absorb a number of water molecules when compared to that normal glass fiber or silica fiber or whatever it may be. So it's one of the drawback when we are going for a fiber composites. We are trying to enhance that in further studies by sodium hydroxide treatment, surface treatment. We will do it, and we have to overcome that.
Okay, Tamil Selvan. In this team, the session people, participants, you have any questions, please ask Tamil Selvan. Otherwise, let him leave.
Any question from participant side? Any questions? Okay. Thank you, Tamil Selvan. Thank you.
Thank you, Arun sir. Thank you, Ramesh sir. Doctor.
Next, Sujitra ma'am.
Yeah, this is Sucharita, sir.
Okay. Sorry. Ma'am, you are ready, ma'am?
Yeah, I'm ready, sir.
Okay. You can present.
Sir, small doubt, sir. Where I can show my screen?
Ma'am, there is if you are using a mobile or laptop.
No, laptop only, sir.
There is an option, ma'am.
Present now.
Yes, ma'am. Screen share. Present screen. There is an option.
Arun, what happened?
Yeah.
Sujitra ma'am.
Just sir. Tell me, sir.
Okay. Any issues?
Yeah, shade I'm giving, but it is not showing my screen.
Ma'am, minimize your.
Sir?
Ma'am, can you? Ma'am, can you hear me?
Yeah.
Any issues in your presentation?
Yeah. I'm sharing my screen, but it is not showing, sir.
Yes, ma'am. Your screen is not visible. Okay. So please check next. Sadasivam sir, you are ready?
Sir.
You are ready now?
Yes, sir, I am ready, sir. 1 minute.
Okay.
Sir,
Ma'am,
are you able to see my screen?
no, ma'am, no, ma'am. Your screen is not. Yeah, now. Okay, okay. Just, Sadasiv, sir, sorry, wait for.
No problem, sir.
Otherwise,
Yeah.
otherwise I can wait.
Okay, okay. You proceed, ma'am. You proceed.
Yeah, yeah. Thank you, sir. Good afternoon, sir, Dr. Ramesh, sir, and all of you who are present here. Yeah, this is Sucharita. I'm from Bharat University, Chennai. These two are Dr. B. Ravishankar and Uma Maheshwar. Those are my other colleagues. So my title is Experimental Investigations on the Effect of Tool Rotational Speed on Mechanical Properties and Microstructure of Friction Stir Welded Magnesium Alloy. This magnesium alloy I have taken as AZ31. Yeah, actually my objective is to investigate the impact of parameters of the tool, rotational speed, feed, axial force on means where on tensile strength or hardness or microstructure, how it is getting influenced. So this is general diagram for FSW, friction stir welding. Actually, here what it is happening, the tool it will move on the base plates so that friction will develop in between the tool and workpiece so that the temperature distribution it will happen on the surface of the plate. The welding it is happening. So this is the general introduction. The friction developed in between the tool and workpiece. Actually, here I have taken magnesium alloys. This friction stir welding is for all the lightweight alloys. Much work has been done on aluminum alloys, so I have taken here magnesium alloy as MG AJ31. Here, general features of magnesium alloys. This is excellent specific strength, excellent sound damping capacity, good castability, hard formability, excellent machinability. All these are so by using all these points, we can replace the aluminum alloys with magnesium alloys. So applications of magnesium alloys
Ma'am,
here pure.
yeah, ma'am, please enlarge your screen, ma'am. Your screen is not that
Yeah.
big.
Hi.
Please slideshow. Okay.
Is it okay, sir?
Yeah, yeah. Fine. Thank you.
Yeah, applications as a pure pure magnesium we can use for manufacturing of aerospace or automotive parts. But when we are alloying with some other particles, we may improve the efficiency of that particular alloy. So some of the most common alloyed elements I have given here: aluminum, zinc, cerium, silver, thorium, etc. And when we are using the magnesium as an alloy in car design or aerospace particles, even engines, typical automotive applications, there we can use this magnesium alloys. Actually, I have taken some literature survey. Means here, all lightweight well alloys, we can use this friction stir welding. So for that, I have taken this. Dr. Saville, he has done much work on magnesium alloys. So what he has given us, when we are increasing the rotational speed, the tensile strength it will get increased, and axial force, axial load, or axial force also, it is acting as a important parameter. And so here, when I am coming to my experimental details, here I have taken the tool as H13 and the tool dimensions as actually I will show you. The pin diameter is 6 mm, the shoulder diameter as 18 mm, and the material I have selected as AJ31. For this, what are the welding parameters I have taken as tool rotational speed only variable here. Three different types of tool rotational speeds I have taken. Those are as 900, 1120, 1400, and again feed, axial force, tilt angle, all are this 30, axial force is 5, and the tilt angle is 1. And here the welding has been done by considering already have given the details. Actually, I have done this work on vertical milling machine. So this is the tool diagram, and this is the diagram for after welding. And here I have done that tensile test as well as hardness and microstructure. Yeah, after performing this tensile test on specimens at 900, 1120 and 1400 RPM, constant feed rate 30 mm per minute and constant load 5 kilonewtons. So I already have given that diagram. At lower tool rotational speed, TRS means tool rotational speed of 900 RPM. Ultimate tensile strength of the joint is low due to lower heat input per unit length. Actually, the friction when it is developing in between the tool and workpiece, if it is getting the rotational speed, it is getting increased. The temperature distribution on the surface of the plate, it is getting increased. Keep on. If lower speeds, the tensile strength we are getting as low. At more speeds, means more than 1400 like that, again the tensile strength it is getting decreased. Why? Because proper heat distribution, it should be there on the surface of the workpiece. So at a tool rotational speed of 1120 RPM, ultimate tensile strength of the joint is high and joint efficiency also more. Yeah, here I am showing my values. 900, all these are constants. And ultimate tensile strength here I am getting as 91.58, hardness as 66.2. As I told, at moderate speeds, at moderate tool rotational speeds, we are getting high tensile strength compared than lower speeds as well as higher speeds. So when I am plotting a graph between tensile strength and hardness to tool rotational speed, I have taken as tool rotational speed and y-axis tensile strength. So here we can see by using these details, it is getting at moderate speed only the ultimate tensile strength it is more, and when we are increasing the tool rotational speed, the tensile strength it is getting less. And every area exhibits distinct capabilities of microstructure depending upon the thermal and mechanical situations. Actually, if proper temperature or thermal conductivity it is appropriate, or proper distribution is there on the surface, means there is no question of intermetallic compounds. When the cooling rate it is getting increased, means when the tool rotational speed it is getting reduced, that time intermetallic compounds will happen. That time when we are when we are going with the hardness test, even hardness also it is getting decreased as I have shown in the values. Here at 966.2, 1120, 64.9, for at 1400, 65.5. And here, thermomechanically affected zone, where the combined outcomes of thermal and plastic deformation have been energetically composed of the unique dendrite grain shape. Dendrite grain shape, where the temperature distribution is proper, then there we can get the dendrite grain size. That time, the ultimate tensile strength also it will be more because of grain size. The unique dendrite shape of being got absolutely disappeared. Actually, when we are starting the friction stir welding, the tool pin, whatever we have taken 6 mm diameter, fully merged with that workpiece. So, if more speeds we are using, means the pin it may vanish. And here I have taken some analysis. Means here I have taken for 900 as well as 1120 only. Why? Because at 1400 I got very less tensile strength, so I have gone through this 900 and 1120. Actually, at 1120 I got a good tensile strength and a good microstructure. Dendrite grain size, as already I have informed. Here, this white color, whatever microns we have taken, where it is showing as this one, those are um, I have observed as intermetallic compounds. And here this is for 1120 RPM. So here compare those 900 images here, the proper surface it has been there, and comparatively that intermetallic compounds are less. And I have taken this index also, energy dispersive X-ray analysis, aluminum, magnesium, intermetallic compounds, and ferrous oxide. Here, ferrous oxide and aluminum, magnesium compounds occurred at peaks at a tool rotational speed of 1120. And the intermetallic compounds have like this needle shape containing increase in stress concentration. If it is again more speed, it is getting increased, it may be which leads to loss of strength. The higher rotational speed causes release of stored material to the upper surface. Actually, this is happening while doing the friction stir welding, and which produces micro voids in the steel zone, and this may be one of the reason for lower tensile properties, as we have discussed for 900 as well as 1400. And joints at lower rotational speed 900 results in lower tensile properties due to lack of stirring and lower heat input. Lack of stirring and a lower heat input, when it will happen? When the tool rotational speed is less. It is observed that the joint fabricated at a tool rotational speed of 1120 RPM exhibited higher tensile strength. This may be due to optimum heat generation, which is sufficient to cause free flow of plasticized material and adequate mechanical work. And here conclusions by doing this one. High tensile strength was observed when the joint was welded at a tool rotational speed of 1120 RPM and a 900, 1400. Compare than these two. The grain size reduction also has taken appreciable change at the speed of 1120. So, due to the appreciable reduction in grain size, high tensile strength was noted at a tool rotational speed 1120 RPM. So here I am concluding as compare than lower speeds or very high speeds, the moderate speeds will be better for getting high tensile strength as well as good grain structure and hardness wise. And, these are the references I have taken.
Okay, Susarita, right?
Sucharita.
Sucharita. Okay, thank you for your time and presentation. And I would like to call any participants. You have any questions? Ask Sucharita.
Any questions from participant side?
So if it is there is no question.
Ramesh sir.
Yeah.
Yes sir. Myself Abhay Gupta.
Yeah, please carry on.
Yesterday because of some problem, I cannot present my presentation. Can I present my right now?
Yeah, Arun Kumar,
Sir,
how is it
availability? Okay, sir. I will check, sir.
Okay,
Gupta, sir, please for 5 minutes. I will inform, sir.
Okay, sir. Please, sir.
Okay, sir.
Okay. Susharita, what is new in your work? Tell me.
Sir, actually,
there are a lot of work have been done in the field of friction stir welding.
Yeah.
So what is new in your work?
Actually, I have started this work for going with submerged friction stir welding of magnesium alloys. So before that, I have started this one.
Trial test.
Yeah. Yes, sir. Okay. And I am going to compare normal friction stir welding, submerged friction stir welding with water and as well as nanofluids.
Okay.
I am doing that work also. Just last month I have given one review paper, and this one. Before going to that work, I want to confirm whether it is getting increasing or not at moderate speeds.
Okay. Okay, because then this is a preliminary work only, but
Yeah,
you need to go for some that what submerged stir welding,
yeah,
no?
submerged. Yeah,
That
already I have completed that one also, but it is in testing conditions, sir.
okay. Where the facility is there?
In Hyderabad.
In Hyderabad.
Yeah.
Okay. Okay,
Actually,
Susarita.
there they don't have facility, just they are having that vertical milling machine only. I myself, I have seen this Anna University. Anna University, it is there, sir, in Chennai.
Okay.
So I have taken that details and all. I have made myself that tub and all.
Okay.
I have done that work.
Okay, Susarita. Thank you.
Thank you, sir. Thank you so
Thank you.
much.
Thank you, ma'am.
Arun Kumar.
Thank you,
Yes, sir.
sir.
Actually,
Yes, sir.
I want the 10 minutes only. The presentation is time is 10
Okay,
minutes
okay.
and interaction maybe 2 minutes. Okay.
Okay, sir. Okay, sir.
Make it
Okay,
short.
okay. Common instruction to all: 10 minutes your presentation and 2 minutes discussion form. Okay. So, Sadasivam, sir.
Sir,
Sadasivam,
yes, sir. Yeah, I'm ready.
sir, are you ready, sir?
Yeah, yes, sir, I'm ready.
Okay, you can present now.
Yeah, shall I start? Shall I share my screen, sir?
Okay, sir. 10 minutes only presentation. Please maintain the time. Okay.
Yeah,
Okay.
sorry, Sadasivan, can you show your face for a minute? Then you can start presenting.
Yeah, sure, sir. Yeah,
Because
no problem.
the people, other participants, they may see your face.
Yeah, sure, sir. Is my face visible? I don't know, sir. Because I'm sitting near a window.
Okay. Yeah. You are visible to me. No problem. What about
Yes,
participants?
sir.
They may be happy, right? Okay. Now you can start your presentation.
Yes, sir. Thank you. So actually, for quite some time, we are working on cold forming of metals. Metals and my guide, Dr. Balasubramanian. But actually, due to this lockdown, we were unable to move out and carry out a lot of work. So I thought of doing a review with more and more exposure. So the title of my work is. So there are a lot of my area of my research is severe plastic deformation. So, sir, is my screen visible to you, sir?
Yeah, visible. No problem.
Yeah, sure. Okay, I am working on severe plastic deformation of materials. I am working on aluminum alloys, especially the 6 series. So there are a lot of methods available to process bulk materials, but actually the application of tubular materials are very widely used. So I thought of doing a review on the processes available. So actually, this field, severe plastic deformation, relies on it is a strengthening mechanism. We strengthen the material by means of strain hardening. So the material that we put it through this process comes out with the ultrafine grain structure, and the morphology of the grain totally changes with the enhanced dislocation density. So that is how my material gets normally strengthened. So we can go up to even nano range of grain sizes. Relies strain hardening is actually what happens. So I've given just a definition of what is strain hardening. So, uh, so these are some plots of what happens to a material when I put it on to make it undergo plastic deformation. So if I put let us take a FCC metal. If I if I process copper to some plastic range, some 10 percentage of cold work, I get a small, a significant enhancement in the yield strength, tensile strength, and but it is accompanied with a drop in ductility. So that is a very undeniable fact. We lose some ductility for that. So it depends on what is our application. So we can tailor make materials with required properties. We can take a metal and make it stronger. So there are a variety of material, severe classification processes. I have listed a very few that I know. There are hardly around 60 process, 55 to 60 SPD processes available. So I am working primarily. I am working on this equal channel angular processing of materials, series alloys. So there are many other materials. There are n number of methods available, but the problem is most of these methods concentrate on processing of bulk material. Industrial application of tubular materials is very high. So when I make a tube, stronger material. The material is much stronger. I can reduce the wall thickness. So that is the aim of making a tubular speedy process. So I thought of doing a small review on the process available in the current literature for doing a tubular. So this is my area of my research, equal channel angular processing. So it consists of an entry channel. You put a workpiece into this and close the die. It's a symmetric die, mirror symmetric two split die. You apply load with the punch. The material gets sheared out. So this creates a lot of grain refinement, grain elongation. So one pass of ECAP is not good. The cross section remains constant, so we can keep repeating this process. It can be done in a consecutively same fashion, or the workpiece can be rotated between process, creating a difference in the grain morphology. A number of variations are possible in this process. So a small photograph of again, this is everything I am showing is from literature. It's not mine. So a small photograph showing it's taken from this my reference. It's showing the material flow pattern, how the material flows. A grid was inscribed and then it was subjected to ECAP. So it's something like a real-time FEA. It shows us how the grid starts, how the process happens. So now, why I am talking about this process again? This equal channel angular processing was modified to perform tubular materials, process materials. So first, in place, I'm just explaining what is ECAP. So it gives us a nano range grain structure with some considerable on 3 to 4 passes. We can go to the nano range of grain size, which gives you substantially high mechanical properties. But the problem is you always lose the ductility. We can see in the 10 image, you can see the pileup of dislocations near the boundaries and the initiation of you can see subgrains are forming. So if we keep processing multiple number of processes, these subgrains in turn become individual grains, and that's how that is a mechanism of grain refinement. So all these dislocations that get piled up add to your strength. So that is a grain bone strengthening. It's another method of making a material stronger. So again, all these images are taken from the references I've quoted in the pattern. So again, this SI pattern also we can see a variety of texturing is happening. The materials are what to say, straining is happening. If we keep repeating the cycles, the stretching of grains happen in almost a variety of directions. So that SIAD pattern tells me what are all the dominant Miller indices where the Miller directions in which your grain is getting aligned. So too much of texturing in a single direction will make your material weak in a particular perpendicular direction. So this ECAP was modified in a way. A tubular material was taken and it was filled with sand and it was processed by ECAP, CP commercially pure aluminum tubes, 20 mm diameter, 13 mm ID internal diameter. So this process parameter here it's not S25. This the angle between these L channels is called phi. So here it is in this paper they have used it as 25, but generally it is called as phi, 150 degree. So this is your 30 degree. Normally this is around 10 to 15, but here they have kept it very large because you are putting sand inside, and it's going to create a huge burden on the press. So they have given you a lot of a high amount of fillet for you to go. This is normally called as corner angle, and this is called channel angle. So 3 passes of ECAP were carried out. Now these routes A, BA, BC, and C. So these are the differences in the method. When I put it as it is for the second time and press it, it's called method A. When I rotate the job about its axis 90 degree between passes, it is BA. 180 degree in alternate directions between next 2, 3, 4 passes, it is BC. Like that. So the variety of possibilities are there. So that is going to result in a very different grain texture. Plastic strain imported. So there is no change in cross section of the material. So normally we cannot measure the strain here, but we can analyze it and we can find it out by some numerical methods and the simulation, finite element simulations, and then we can validate the simulation by taking the we can take micro hardness values across the cross section and the trend of variation can be compared with the finite element strain contour, we can validate our simulation. That's how normally people do validate their FEA simulations with the real test, because we cannot directly measure the strain here because it's a non-measurable, no cross-section change. Same cross-section is maintained after the process. Strain is not measurable here. So it comes around some 0.3 plastic strain is important in each pass of this process. So I'm restricting my discussion with the process methods and a few accompanying by some mechanical properties. I'm not going into microstructure. So these routes were followed, and found that route BA was found to give me highest amount of hardness, and it was quite comparable. Not much of a difference in the processing route. Processing was carried only up to 3 passes. So this is one method to perform hollow ECAP. The second method is I'm taking this is an integrated extrusion ECAP, where a small extrusion is happening before your ECAP actually. So there is one extrusion happening here, small reduction in diameter, after which you can have one pass of ECAP and the next consecutive pass here. Here you have one shear, and the second shear is happening here. So what I do is I am taking a copper tube. So this is your copper tube, and it is fitted in with a lead core. So because you cannot directly plastically deform a tube, it will buckle when it changes the direction. It will break, shearing, or some type of failure will occur on the walls of the tube. So we are fitting in a lead core or a lead mantle, and it is processed along with the lead is a sacrificial part. You have to throw it away. You can melt it outside very easily. So this method was followed for performing ECAP of copper tubes. So 14 mm dia tubes, 2 mm wall thickness. Lead was used as core. Extruded from 14 to 7 mm in the first step, imparting a 1.4 plastic strain. Then 2 consecutive ECAP passes. Each ECAP pass imparted a 0.8 plastic strain. So the die used here has a channel angle of 120 degree and a corner angle of 0 degree. It's very sharp corner, 0 degree. So total cumulative plastic strain imparted here is 3. So the higher the plastic strain, the better will be your strength enhancement, strengthening. But along with that, you will lose your ductility. So you have to know where to stop. So that is very important. Tubular ECAP with another method where I fit the ends of the tube with some threaded lids, and I fill it with the SAE 30 hydraulic oil, and then I do the same. It's somewhat similar to the first method, but here instead of sand, I am putting in hydraulic oil. Here 6061 tubes, 10 mm outer diameter were processed in a ECAP die, 120 degree channel angle and the corner angle 22 degree. Tubes filled with SAE hydraulic oil, SAE 30 grade hydraulic oil. Each step of ECAP imported a 0.63 magnitude of plastic strain. So after ECAP, I am performing a T6 heat treatment. So the parameters of the heat treatment are given here: 520 degrees Celsius solution treatment, after which I water quench, and then artificial aging at 8 hours at 170 degrees Celsius. The hydrostatic stress present inside the tube actually didn't work out in the way they thought. It led to a small ovality in the cross section. Thinning of the tube was found at the head, and thickening was happening near the head section, and thinning was. Some work has to be done on this. Continuing this work, we have to do some more work on this to refine the process. So the testing of this material was carried out. Shear strength. I mean, the torsion test was carried out because tensile test was not done in this particular work. They done the torsion test. So yield shear strength and ultimate shear strength improved by factor some 250% improvement in yield, and 140% improvement in ultimate shear strength was found after this ECAP. Heat treatment further improved the ductility of the sample. Strength is meaningless if you have very brittle material. It is, of course, we can improve the strength, but you cannot lose all the ductility. So hardness values improved by a factor of 2.1. That is 210% improvement. Further improvements were possible after heat treatment because of the 6 series alloy, heat treatable precipitation hardenable alloy. Next work is your. This is a. I believe I have some more time. HECC. Actually, so it's like a hollow extrusion. The workpiece is forced to flow through the entire container is filled with oil. I press the billet and make it to flow outwards, so that I end up with a tube of a larger diameter. So here you can see there is one ECAP pass happening here and another ECAP pass happening here. So this is a what is it? Outward flow ECAP, hydrostatic reverse hydrostatic back pressure was applied on magnesium AZ80 alloy. 60 mm tubes of 400 mm length were actually taken, and this 60 mm, it's not a tube, it's a billet, and this billet was formed at 290 degrees Celsius forming temperature, because magnesium is brittle and it's difficult to form it at room temperature. We need 290. So 3 different extrusion ratios were used, bringing out tubes of same outer dia but different inner diameters. Conical mandrel was used to create that obstruction for extrusion of the tube. Extrusion container was heated at temperature was maintained at 220 to avoid chilling at the die contact surface. The highest extrusion ratio produced some good strength enhancement. So the 308 MPa of yield strength, 335 MPa of ultimate tensile strength, and percentage of elongation of 7.2 is good for magnesium. It improved the hydraulic back pressure that this castor oil is giving. Here, if you can see, this entire thing is filled with oil. There is some back pressure exerted, which is homogenizing the forming load.
Okay. Sadasivan, let us stop the presentation. You can show the remaining slides.
Shall I move the slides, sir?
Yeah, move the slide.
Okay. So the next process, here are actually 3 different forming steps happen in a single go, and this can be repeated by rotating the die upside down. It can be done any number of times we want. Something similar to this, but the corners of the die are very sharp. Here it's called tube channel angular pressing. It's a combined technique where parallel tubular channel angular pressing, the first method with the 2 green dies, and the last one is a tube backward extrusion. 2 methods were combined together, and tube and this magnesium alloys, 20 mm tubes are processed in this, and they found to produce good results. Some combined process produced 133% enhancement of yield strength, 26% of ultimate tensile strength, and a drop of ductility, 12%. So it's a direct process, very short tubes. So again, why I've reviewed all these things. What I found out by reviewing all these works is that there is a lot of research gap available if we can start working on these things, because tubes are very highly used. Tubular products are used every day. So there are a lot of research scope is available in these cold forming areas. So much of work is left uncontinued. So much of research gap is available for people to come here and start. So that's what I found out by doing this small. It's a very small review actually. Due to the restriction on the length of the article, I was unable to include the metallurgical aspects of this all the work. It is even more interesting if we look from the metallurgical point of view. So I'll stop here, and I'm happy to answer if there is any.
Okay. From any questions from participants? Yeah, I can assume that there is no question. Sadasivan, actually, you said it is a review paper, right?
Yes, sir. Yes, sir.
But I found only 12 papers you reviewed.
Yes, sir.
Hope you know what is review paper, right?
Yes, sir. Yes, sir.
Even, so this is your initial stage of your research, or what is the level?
Actually, I'm about 7th semester of my research, sir.
7th semester of your research?
Yeah, yes, sir. It's a very small work, actually.
Then it is very small work, and the review paper, what you have given it is not up to the standard of your guide. Okay.
Sir, actually, we published a review paper on ECAP last month, sir, in elsewhere. But this work is a very small work. This is not my core area. It's ancillary work.
Yes.
Because there was a severe restriction on the length of the manuscript, I was unable to bring in a lot of things.
Okay, thank you.
Yes, sir.
Yeah.
Thank
Next,
you, sir.
Arunpa,
Thank
next.
you. Thank you, sir. So, anybody from enzyme modified electrodes for biofuel cells, a comprehensive review for Professor Ramesh, sir. Enzyme modified electrodes for biofuel cells, a comprehensive review. Okay. Optimization of drilling output responses of Excel fillers.
Hello, sir. It's the Ramesh from Enzymatic Biofuel Cells.
Okay. Enzyme
Enzyme,
modified electrodes
enzyme,
for
yes, sir. Biofuel cells.
Professor M. Ramesh.
Yes, sir.
Okay. Okay, sir. You can present.
Uh, so good afternoon, sir. It's a review paper about the enzyme modified biofuel cells. Usually, the biofuel cells are using different types of catalytes, which is mines like that and all. It making it is making the process costly, and it's somewhat like polluting the industry, that means environment too. So we are going for different types of catalysts in the biofuel cells. For that, we are going for enzymes. Enzymes are very much easy for production, and it can be produced in mass.
Dana Prabhu, can you show your video also?
Yes, sir. Yes, sir.
Yes.
So we are going for different types of enzymes which can be used with the fuel cells. The enzymes are the main things which can be convert the fuel substrates into the which can be convert the fuel substrates into electrons and the protons, which can be transferred to the anode from anode to the cathode to produce electricity. So we are going for enzymatic fuel cells. Usually, sir.
Sir, your paper is not visible.
Yes, sir. 1 second, sir. Sir, is it visible, sir?
Yeah. Go ahead. Now it's go.
Okay,
Make it full screen. That's fine.
Okay, sir. So we are going for the biological enzymes for the production of the electricity through the fuel cells. Basically, when we consider enzymes in the fuel cells, there are two types of transfer of electrons, which has to be considered as a main thing if when we consider enzyme as a catalyst for biofuel cells, which is direct electron transfer. When the electrons transfer between the enzymes and the electrodes in a direct manner, means it will be very efficient. There will not be any losses and all. But when we consider through the mediator, means there may be some losses through the mediators, and the efficiency will get less. When considered enzyme, means we are giving fuel substrates to the enzymes. The enzymes convert the fuel substrates into different compounds at the active centers. So the active centers, where we are placing the active centers and considering the active centers in the enzymes, is also an important thing which we have to consider. And the active centers should be the total enzyme should be immobilized. When it is in movement, means the reactions will takes a lot of time to take to produce the compounds. So first the enzyme should be immobilized. That means we should lock the movement of the enzymes, and after that the fixing the active centers where the fuel substrates is converting into the compounds. When the active centers are at the edge of the enzymes, means it's very tough to transfer the electrons from enzymes to the electrodes. So we are going for the centered active centers. We are using it for the maximum efficiency. And we are going for the mediator electron transfers also, where the active transfer is not possible or somewhat tough. So we are using usually in enzymatic biofuel cells, means we are utilizing the electrons for breakdown. We are utilizing the electrons by breaking down the fuel substrates from the through the enzymes, and after that we are transferring the compounds, that means electrons and protons and molecules, to the uh, fuel cells through the mediator or without the mediator. If we are not using the mediator, means the active center should be closer to the electrodes. That means we should place the active centers closer to the electrodes for the better transfer of the electrons without any losses and for the better efficiency. So these are the diagrams for the normal conventional fuel cells and the difference between the conventional fuel cells and the enzyme-based biofuel cells. Most of the papers has been considered the same type. Most of the papers consider the glucose as an catalyst for catalyst as an enzyme catalyst, and some of them gone for the carbon nanotubes combined with the glucoses and all. And here we can see that in the conventional fuel cells there is an we are using metals as a catalyst, and in by enzymatic biofuel cells we can see the enzymes are surrounded with the electrodes. We are giving the fuels to the enzymes. We are giving fuel substrates to the enzymes, and the enzymes are at the active centers. The enzymes, that means the fuel substrates, will get converted into products, and the product is transferred to the uh, fuel cells, that means electrodes, and it has been transferred to uh, the cathode. During the transfer of the process, the electrons are given to the outer product where we need electricity. We are using two types of enzymes, the oxidizing enzymes and the redox enzymes. In the oxidizing, at the anode, we are using oxidizing enzymes, and at the cathode, we are using the reducing enzymes. And for the immobilization, already we have discussed about that, and we should immobilize the enzymes. When the enzymes are in movement, means there is lot of chances for the losses of electrons, or the reactions may get take and delay. So we are going for the immobilization. For immobilization, we are using four types of techniques: adsorptions, entrapment, and cross-linking, and covalent bonding. During the adsorption process, we are dipping the electrodes inside the enzyme solutions. In the enzymatic solutions, when the enzymatic solutions, when we dip the electrodes in the enzymatic solutions, means it may adhere, and it may lose or dry during the biofuel cell process. So it may not be a correct process for a long time bio fuel cell process and all. So we are going for different methods: entrapment and cross-linking and covalent bondings and all. In adsorption process, we can see that we are dipping the electrodes inside the enzymatic biofuel cells, so it may not stick into the fuel cells. The immobilization will be very less, then it may mobilize. The enzymes may mobilize and may dry up also. So we are going for chemical cross-linking and entrapments and all. We are totally locking the movement of the enzymes and making it as an making to stand there. So the fuel substrates can be easily convertible, and the electrons can be easily movable to the electrodes. So the electrons transfer after converting the fuel substrates. Already the enzyme has been immobilized, and the fuel substrates has been converted into products. So we have to transfer the electrons to the electrodes. So we are going for direct electron transfer and mediator electron transfer. When the direct electron transfer takes places and all, there is the active center should be at the center of the molecules. So it can be easy for the fuel substrates to convert it into products, and the products can be easily, that means the electrons can be easily transferred to the electrodes. In the mediator and electron transfer, it differs means it's in two types of layers: mono layers and the multi-layer structures and all. In mono layers, we are using enzymes and then mediator, which is used as an oxidizing mediator. It has to transfer when the active center is at the edge of the enzyme, means we have to use the mediators for the transfer of the electrons to the fuel electrodes. So we are using the mediators, and the mediators should be very efficient, and it should also immobilized for the better movement of electrons. So in the mediators, we are choosing the mediators as the enzymes. So we have to choose the mediators based on the enzymes, which has to support the reactions and all. It should not have any interreactions and all. So we are going for the mediator and electron transfers, but as far the efficiency is considered, the direct electron transfer is better for the process, and mediator and electron transfer can be used where the direct electron transfer is not usable or avoidable. So, and these are the enzymes locking, that means immobilizing techniques, where the crossing, it's an intermolecular and intermolecular and intersubunit techniques, where it can be when the temperature is considered, it is a bioelectro process. So the enzymes cannot withstand at higher temperatures. So we are using it as a combined one. When it is in individual things and all, it cannot withstand the temperature. So we are combining it and making and bonding things. So it cannot immobilize, and also it can withstand the temperatures. So we are going for cross linker agent to bonding it for it. It's layered structures and polymer matrix. As we have already told that the layered structures means we are using the enzyme and mediator and the electrodes. In the layered structures, we are having monolayers and multi-layers. In the monolayers, we are using a single mediator, and we are going for the transfer of the electrons. In the layered structures, we can use 2 to 3 mediators which can transfer the electrons. But when we have to consider each mediators, that means which mediator is we going to use for the first one and the second one, like that. And also for convert, it's like a sandwich like appearance, so we have to maintain the enzymes and the mediators in a particular manner. So and for immobilization also, or converting the for immobilization and for the better performance, we can also convert the amino acids. We can change the amino acids through direct mutagenesis process. So through direct mutagenesis process means we are changing the genes of the enzymes. When the genes of the enzymes is changed means it may convert it may resist something. It may change the resistance of the electron. That means it may change the resistance of the current at the active centers. So we are going for direct mutagenesis process, and we are also going for amino acid substitutions, which is also used for the direct that means change the properties. And we are going for amino acid removals, which is also which also resists some current densities. That means change the resistance of the current densities and the movement of the current or electrons, movement of the electrons. So the amino acid concentration is also an important role for mobilization movement of the electrons. So we have considered three things under direct mutagenesis and the removal of the amino acids and amino acid substitutions. Three of them will will change the properties of the enzymes, and when the properties of the enzymes is changed, it will change the immobilization property and the movement of the electrons. So through different papers we have gone through that. We have considered the glucose based and the glucose based biofuel cells. When the time increased during the biochemical process, we have already discussed that in which method we are using to stick the enzymes with the biofuel electrons. So if it is an adsorptive process, it may, during the when the time takes place, that adsorbed enzymes may fall out. So we are going for, based on the time, the power output is getting on decreasing because the enzymes are losing its life. It can't withstand for a longer life. And at the same time, the temperature, when the temperature rises also, the enzymes can't withstand. And during the sticking, the immobilization process, when it fails, or we are using adsorption process, means it may fall or dry up. So when the time goes by, the power output is falling. So in the next thing, we are used immobilized GOX, that means glucose oxides, and immobilized and cross-linked glucose oxides. We have used the immobilization process with two methods, with the entrapment and cross-linked, like chemical reactions with the molecules, and we are cross-linking the process.
Okay, Dhanaprabhu, your time is over. Already I gave 2 minutes extra. You can make it complete the slides.
Okay, sir.
Yeah, just pause the slides.
Sir, it's performance of biofuel cells using the glucose concentration. Whenever the glucose concentration rises, the fuel substrates, you can, when the fuel concentration, that means glucose concentration, the fuel substrate rises, means the current density also rises, because we are using enzymes which will convert the fuel substrates into electrons. So here the glucose concentration, the fuel substrate increases, means it is converting the glucose into electrons. So we can see that the graph is rising with glucose concentration. That's it, sir. Thank you.
Yeah, from participants, is there any questions to Dhanaprabhu? Okay, Dhanaprabhu, it's a nice work from your side. So what is your contribution in this work?
Sir, we have reviewed the papers and we are going for a prototype, sir, but due to lockdowns and all, we can't proceed with that. So we will slowly move on with that, sir.
So you registered a PhD under Dr. Ramesh?
No, sir, not yet, but we are planning for it, sir. I'm planning for it, sir.
Okay. So that means this is not your PhD work?
No, sir.
Oh, okay. Okay, anyway, it's a nice initiative job. Okay, good.
Okay, sir.
Keep it up. Thank you.
Thank you, sir.
Thank you, Dhanaprabhu. Thank you, sir.
Thank you, sir.
Okay. So anybody belongs to this paper, optimization of drilling output responses of Excel fillers, reinforced shell, glass fibers, hybrid fiber composites for Professor Ramesh. So, so Dr. Rakesh Singh, sir, what is your paper ID, sir?
Yes, sir. My one of the co-author Nishant Kumar will present the paper. He is on the line.
Okay. So what is your paper ID, sir? Your paper ID is not in the schedule.
Not schedule.
Yes. What is your paper ID, sir?
Nishant ji, you are online?
No, sir. So Nishant is not in the line, sir. Okay. Jnana Dilip Bandaru. Sir, Jnana Dilip Bandaru. Sir. Jnana Dilip.
Yes, sir. This is Bhagat Singh. I will present the paper, sir.
Okay, so what is your paper ID, sir?
Just wait, sir.
Because your paper is not in the schedule, that's why asking. Discuss with Punchan, sir.
But Arun, I have to complete by 3:50. Okay.
Okay, sir. Okay, sir. Okay, Bhagat sir, please send your paper ID and title.
Sir, I will send the title now.
Okay, sir. Ramesh sir. Sir, sir, present பண்ண இது பண்ணணுமா சார்? பண்ணட்டுமா?
இல்ல இப்ப ஆக்சுவலி
இல்ல இந்த எக்ஸ்ட்ரா 2 பேப்பர் வந்து அவர் வந்து சொல்லியிருந்தாரு கோஆர்டினேட்டர் சார். அதான் இவர் ஒருத்தர்.
No, anybody is waiting for presenting the paper?
No, sir. No, sir.
Yes, sir. This is Bhagat Singh is waiting for presenting the paper.
Bhagat Singh is waiting for the presentation, right?
Yes, sir.
Okay.
Yes,
okay.
Sir.
Let him start the work. No problem.
Okay, sir. Anyways, I will stick to the timings. I will not take more than 10 minutes. So I will finish it.
Okay, sir.
So my screen is visible now.
Going to visible. Yes, make it a full screen.
Is it, sir? Okay, right. So yes, this is Bhagat Singh, working as an associate professor and under the Department of Mechanical Engineering in the College of DBR and Dr. ICMSD College of Technology, Vijayawada. So the co-authors are Sangameshwaran, Prem Kumar, and Jnana Dilip. So here we are going to discuss about the effect of basalt powder in the aluminum 5083 alloy. So generally, we have seen a couple, for the past decades, we have seen quite a number of research have been done on the mechanical property of composites, especially on the aluminum-based metamolysis composites. So this is a work which is significant in the terms of selecting the reinforcement. So you could have noticed so many research articles in the areas of aluminum metasomatic composites, selecting reinforcement as silicon carbide, aluminum oxide. There are plenty of reinforcements being checked and tested very effectively. So this is one of the another attempt to test the mechanical property of aluminum-based composite by choosing basalt powder as one of the major reinforcement. So this is a significant attempt what we are going to do. So we will see one by one. So the presentation goes like this: the introduction, objectives, applications, of MMC's method of production, composition, dimensions, and results of discussion. So we know that the people are aware that major advantage of composites is like a very high strength, and we can go, if you go with aluminum based metal matrix composites, that will give you a wide range of advantages, like in terms of strength to weight ratio, and like by adding or manipulating the alloying additions, we can able to improve the mechanical property together with the corrosion resistance, so that we can have a better range of applications. So like the major objective of this research is, like I said, we are going to work on the metal matrix composite, but in this research we are going to choose basalt powder as the like a reinforcement. So what is the thing about the basalt powder? Like what are the other things which are not present in the other reinforcement, and what is the present like in the basalt powder is like. Basalt powder is the combination of so many refractory materials. Like you can see in the second table, you can see that the presence of refractory like silicon oxide, aluminum oxide, iron oxide, calcium oxide, magnesium. So like there are plenty of ceramics are already available inside the basalt powder. And the other thing is that like the basalt powder is available very rich, very able to do so much of extraction work and all. So you can take that rock. Generally the basalt powder is taken from the basalt rock. That once you take on the rock, and you can just crush it in under the press, and you take it as a powder, and you go for this basalt powder, and you can add it in the mixture of molten mixture of any material, and you can make a composite very easily. So this is a significant, like you can get it very cheaply, as well as the availability of ceramic particles inside the significant of this basalt powder. We know that like the aluminum based MMCs are very wide range of applications. Like you can see here this aluminum based this aluminum based composites, like using the Al2O3, like usually are made out of a drive shaft, and you can see this passenger car disc, like which is made out of the silicon carbide particle. So there are plenty of work keep on going on, and very recently the iron-based materials are completely replaced with the aluminum-based metal matrix composite. So in order to add one more feather to the composites, aluminum-based composites, we are working on this development of aluminum-based metal matrix composites using the basalt powder. So we have used the stir casting technique. Anyways, there are plenty of manufacturing methods for the production of the composites are available. Like in the case of powder metallurgy, very recently and very good. Like in the powder metallurgy route, we can able to bypass the amount of alloying additions inside, adding inside the solid solution, because if you are going with the casting method, then there are some limitations about the humidity theory. But by going with the powder metallurgy, we can able to incorporate a lot of ceramic particles. But here we are using this stir casting method, which is very conventional and very effective method for the making of aluminum-based metal matrix composites, especially when you are going for the manufacturing of very complex parts. This is what the major advantage. Like if you are going for making of any automobile engines, definitely we have to use the casting method. There is no other manufacturing method available for the manufacturing of automobile engines. So here also we have used the stir casting technique. So stir casting technique is a very well established technique for the manufacturing of composites. And then the crucible will be heated above the molten temperature. So for this work, we have heated the aluminum 5083 alloy to 700 degrees Celsius. During the heating of the base material, we have preheated the basalt powder. So what is the need for the preheating? Generally, if you are going to add this basalt powder inside the molten metal, directly it will not act as a nucleation agent. So nucleation agent is one of the primary mechanism which is responsible for the grind refinement. The grind refinement is occurring during the solidification. As a result, the strength are improving. So, right. So in order to act as a nucleation, so the whatever the reinforcements you are adding, you should have some some kind of wettability. So wettability is one of the major phenomena which is responsible for the nucleation mechanism. So in order to define the grain size, the basalt powder or the any kind of reinforcement should have proper wettability. So how we can able to improve the wettability? Suppose if you are adding it in the room temperature, the wettability will be very, very low. So if you are increasing the temperature of the reinforcement particle, then the wettability grain refinement to happen. Then we can able to anticipate the increase in the mechanical property. So as a result, we have preheated the reinforcement to 450 degrees Celsius for around 2 hours. Then we started to stir. Once the molten aluminum is ready, we have added the basalt powder. Then once the stirring is happening, so the basalt powder is completely mixed homogeneously. Then after that stirring for nearly 15 minutes, then here. So these are the setup. Once the aluminum is melted, and we have added the basalt powder. After that, we have poured into the dye. So after that, we have followed the same suit for all the 3 compositions. We have taken the basalt powder in 0 and 5% and 10%. So and we have poured into this rectangular dye. And once we have started with the microsection analysis, because this is where you can able to see whether the any kind of action has taken place by the addition of basalt powder. And we can see here the base material having very, very, but once we add 5% of basalt powder, you can see the grains have been refined very much. And once you around the microstructure, as a result, the grains have been also refined. Like in the case of initial microstructure, the grain size is only 15 micrometer, and once you are keep on increasing the basalt powder, the grain size have been reduced, and you can see the fine grains up to 30 micrometer and 20 micrometer with the addition of basalt powder 5% and 10% respectively. So we what we expected has been.
Hello.
Sir, let I turn the network issue.
I think some internet issue it seems.
Yes.
Okay. Okay, maybe another up to 3:45 we can, if you want, we can engage one more person. Otherwise, we can wind up, no problem.
Okay, sir. So, Dr. Rakesh Singh, sir. Sir, Dr. Rakesh Singh, sir. Sir, Dr. Rakesh.
He is searching his scholar, it seems. He is not present here.
Yes, sir. Yes, sir. Rakesh, sir?
Yeah, Nishant
scholar is available.
One of the co-authors will present the papers, sir.
Yes, sir.
He is not available, it seems.
He is not available, sir.
Yeah.
Yeah, he is available.
Is available?
In the name of?
He is available, Nishant Kumar.
No, sir. Nishant Kumar not in the participants.
List, we are checking the list. No name with Nishant Kumar.
Yes, sir. He is on the line.
No, sir. Jnana Dilip Bandar only.
Line पे नहीं है, वो बार-बार कॉल हो रहा है.
Whether he is in this session or some other session.
वो बोल दीजिए ना उसको, मतलब वो बोल दीजिए ना उनको बात. But sir, he is sharing the screen. He is sharing the screen share, Nishant Kumar, on the behalf of my Dr. Rakesh.
Okay, in your login itself, he is doing, sir.
He is trying to connect the screen.
No, sir. Nishant not in the line, not in the room. Not in the meeting room.
Maybe they are working on 2 separate sessions, it seems.
Sir, kindly check with your scholar, sir. Please call him and ask him where.
Yes, sir. He is on line.
Yes, Professor.
He is trying to share the screen.
Yes, Professor, but there are some parallel sessions are going. He may be in some other session.
Okay. What is the time, sir?
What Arun Kumar?
Time,
Sir,
sir.
sir, parallelly going 2 to 4, we have 5
Yes.
sessions, sir. Sir,
Yes, sir.
kindly call him.
What will be the next session will be?
No, no, this is the final session, sir. 2 to 4.
हाँ सर अरे आप दिख ही नहीं रहे ना टेबल में दिख ही नहीं रहे आपका नाम ही नहीं दिख रहा है
Sir, Jnana Dilip Bandaru, sir.
लेकिन अभी आप दिख ही नहीं रहे हैं
Jnana Dilip Bandaru, sir.
So he is left.
Yes, sir. Okay, sir. I think.
Okay, we can wind up. Arun Kumar. I think Dr. Rakesh sir is having some problem with his student. I think he is involving in some other session. It seems.
Yes, yes, sir.
I
Yes,
think
sir.
is there any session-wise ID is given?
Sir, no, sir. There is no. I have only this session.
Only the presenter only knows that which session he is going to
Yes,
present.
sir.
Right?
Yes, sir. Yes, sir. Yes, sir.
Yeah, I think he is trying to some other session.
I think so, sir.
Yes, yes. Okay, Arun Kumar. Okay, because for me I have to complete by 3:45.
Okay, sir.
Okay. So
Sir, before
if
that,
any,
okay, sir. You got a final conclusion? Anything, sir?
Yeah, the conclusion in the sense actually in this session there are I found 5 presenters.
Yes, sir.
Okay, the last presenter is Bhagat Singh, right?
Yes, sir. Bhagat Singh.
He has presented with the MMC composite related thing. And others, whether you are planning to give any best paper award in this?
No, sir.
Not like
no,
that,
sir.
right?
Not like that, sir.
Okay. Anyway, just I entered some mark in my Excel sheet. Okay.
Okay, sir. Okay, sir.
I will share you this Excel sheet. Okay, now you can use
Okay.
this. If any, you can fill the title and everything for others.
Okay.
Also, the
Okay,
two people they entered now.
Okay, sir.
For remaining people, I entered the mark everything. So you
Okay,
can make
sir.
it, no problem. Okay.
Okay, sir. Okay, sir.
Okay, right. All presenters they did nice job, and the work it is really a new advancement topic they have given. So really, I appreciate this conference topics. So thanks for giving me an opportunity to being a session chair for this conference. Thank you very much for your management as well as your convener. Thank you very much. Thank you very much.
Sir, thank you, sir. Thank you for your valuable presence and spend valuable time with us, sir. Thank you, sir. Thank you, sir. Sir, thank you, sir.
Yeah, shall I leave?
Okay, sir. Okay, sir. Okay, sir. Thank you, sir. Okay, thank you to all the participants. You can leave now.